Hello students. So in this video we will be discussing NEET PYQs of chapter magnetic effects of current, right? So let us start. We'll go in the order first 23, 22, 21 and like that. Let us start. Yeah. So the question that is given to us, first question we have is, a very long conducting wire is bent in a semicircular shape from A to B. Okay. As shown in figure, the magnetic field at point P for steady current configuration is given by. Now over here, if you notice carefully, this wire configuration is given to us. In this wire configuration, we have three parts. There are two wires, two straight wires, two long wires, and then there is a semicircular wire. With respect to point P, this wire, I'll name them one semicircular as 2 and the another one as 3, right? Now over here, with respect to point P, wire number 1 and wire number 3 are your semi-infinitely long wire, and this one is your semicircular wire. So let us first of all write down magnetic field due to individual wires, and then we will see the net magnetic field. Let us see. At point P, magnetic field due to wire 1, which I am calling as B1. So B1 will be due to a semi-infinitely long wire. What is our magnetic field? Mu naught I by, how much is our distance r? So mu naught I by 4 pi r. Direction, how do we find out direction of magnetic field due to a straight wire? Thumb in the direction of current and bring the palm to the point P. Palm is facing inward. That means direction of magnetic field is cross circle, which is in inward direction. B3, first I am calculating B3. B3 due to semi-infinitely long wire, mu naught I by 4 pi r, direction wise, thumb in the direction of current, palm faces inward, and so palm faces inward, so again inward direction, both are in inward direction. Let us calculate net of this. B1 plus B3 comes out mu naught I by 4 pi r, mu naught I by 4 pi r, it comes out mu naught I by 2 pi r, both are in inward direction, so directly we added them. Now what is the magnetic field due to this semicircular wire? It is B2 will be mu naught I by 4r. This is the magnetic field due to semicircular wire. Direction wise, turning the thumb, the current is given like this. So turning the thumb in the direction of current, turning the fingers in the direction of current, thumb will give you the direction of magnetic field. Turning the fingers in the direction of current, thumb will give you the direction of magnetic field, where it is coming outward direction, dot circle, right? Now this is inward direction, that is outward direction. As you can notice, magnetic field produced by your semicircular wire is more in magnitude as compared to this one. Therefore our net magnetic field B net will be mu naught I by 4r minus times mu naught I by 2 pi r, right? Direction will be outward, out of the plane, right? So it becomes, if we take common over here, mu naught I by 4r, if we take common, this will be 1 minus 2, it becomes your 2 by pi in outward direction, right? Now take a look at the option. Option number B is our correct answer, that is mu naught I by 4r, 1 minus 2 by pi, pointed out of the plane of paper, है ना? Pointed away from paper. Fine. That means this is our second option is our correct answer. Let us move ahead. Yeah. So our next question is, it says a wire carrying a current I along the positive x-axis has length L. Okay. X-axis, and some wire is there of length L. It carries a current of I. Not specifically mentioned positive x direction or negative x direction, so we will take it plus x direction only, right? It is kept in a magnetic field B vector equals 2i cap plus 3j cap minus 4k cap. 2i cap plus 3j cap minus 4k cap. The magnitude of magnetic force acting on the wire is fine. Magnitude of magnetic force. First of all, what is magnetic force on a current carrying wire in a magnetic field? It is given as force magnetic is I L cross B, IL cross B, which we also write as ILB sin theta. But in this case, we need IL cross B form only. So let us substitute the values. Current I is given, capital I is given in question. So we'll take it I L vector. Now L vector direction will be taken along the direction of current only. L vector direction is taken along the direction of current only, and it is basically it is present along x axis, so it will be L vector direction is your I cap. So what do we get it over here? Over here we get L I cap cross magnetic field, which is 2 I cap plus 3 j cap minus 4 k cap, right? Now let us do the cross product of it. Simply cross product we have to do. I cross I is 0, I cross j is k cap, and this becomes your 3L k cap, right? Next, I cross k is minus j, right? I cross k is minus j, and minus minus is plus, so this becomes 4L j cap. This is what we have got it. Now over here L can be taken common, so we have IL 3k cap plus 4j cap. This is what we have. But they have asked us what? They have asked us the magnitude of it. If we find out force magnetic magnitude of the magnetic force magnitude 3k cap plus 4j cap, if we find out magnitude, it will come out to be 5 root over 3 square plus 4 square, that comes out to be your 5. So ultimately our answer is 5IL. Which option it is? Option number 2 is our correct answer, right? Yeah. So the question that is given to us is, two very long straight parallel conductors A and B carry current 5 ampere and 10 ampere respectively and are separated at a distance of 10 centimeter from each other. Fine. Two long wires are given to us. Two long wires carrying current 5 ampere and 10 ampere, and they are separated by 10 centimeter. Okay, the direction of current in two conductors is same. Okay, I have taken it upward in both of them, same only. The force acting per unit length between two conductors is. Now this is a very standard question, very standard relation. What is the force between two parallel wires? Force between two parallel wires is given by mu naught I1 I2 by 2 pi r. Now this force is basically force per unit length. This relation is force per unit length is given as mu naught I1 I2 by 2 pi r, right? Let us find out the magnitude, then we will see whether it is attractive or repulsive. So let's substitute the value 4 pi into 10 power minus 7. I1 I2, this is given 5 and 10, that means it will be 50 by 2 pi into r. Separation between them is 10 centimeter. 10 into 10 power minus 2, right? So we get over here, this will be 2 times, this is your 5. So we have 5 2 is 10. So 10, and this will come out to be your 10 into 10 power 2 into 10 power minus 7. So what are we left over here? 10 power minus 4. 10 power minus 4. Do we have any option like this? Yes. Option number C and D are this only. Force per unit length is 1 into 10 power minus 4. Now the question is it attractive or repulsive? So basically, if you notice, the simple point that we have to remember is the fact is that if current flows in the same direction, the wires will attract each other. If the current flows in opposite direction, the wires will repel each other. So the answer for this will be 1 into 10 power minus 4 attractive. 1 into 10 power minus 4 attractive. Option will be your option number C will be correct answer. How we got this attractive? Basically, this wire will produce magnetic field in inward direction. This wire will produce magnetic field inward direction along this. Inward is this, right? and due to this inward direction magnetic field, this 10 ampere current carrying wire will experience a force in this direction, right? Similar thing will happen with this also. This wire is producing magnetic field in outward direction and force on this will be towards the wire. So the force on each other is toward the force on both of them is towards each other, right? If the current flowing is in same direction, they will attract. If the current is in opposite direction, they will repel. And this is our, so our answer already we got it. It is C option, right? Yeah. So the question given to us is, a closely packed coil having 1000 turns has an average radius of 62.8 centimeter. So a coil is there. Now how many turns are there? N is 1000 turns are there, and radius is given to us 62.8 centimeter. Fine. Okay. If current carried by wire of coil is 1 ampere, I is 1 ampere, the value of magnetic field produced at the center of coil will be. Now, value of magnetic field produced. What is magnetic field produced by a coil at the center? Magnetic field is given as mu naught I by 2R. But over here it has 1000 turns. That means it becomes your what? Into 1000, which we also write mu naught Ni by 2R or mu naught I by 2R into 1000 due to one turn, due to 1000 turns. Fine. Let us substitute value. So mu naught is 4 pi into 10 power minus 7. Current is 1 into 1000, which is 10 power 3, divided by 2 into R. R is 62.8 centimeter, which becomes 62.8 into 10 power minus 2. Over here pi value is your 3.14. So 4 into 3.14. When we will solve it, our final answer over here will come out to be 10 power minus 3 Tesla, right? When we'll solve it, we'll get it 10 power minus 3 Tesla over here, right? Yes. So the question given to us is, the shape of magnetic field lines due to an infinitely long straight current carrying conductor is. It's a theoretical question, NCERT based question. So let's say a current carrying wire is there, current is I. We have to find out magnetic field lines. What is the magnetic field line shape? Magnetic field lines are circular in nature. Magnetic field lines are circular in nature, which are concentric circles. Which option do we have? Option number 2. Option number 2, they are concentric circles. Yeah. So the next question that is given to us is, a long solenoid of radius 1 mm, a long solenoid, that is infinite solenoid is given, radius is 1 mm, has 100 turns per mm. That is, number of turns are given to us, small n is given to us, 100 turns per mm. Be careful with this. It is not given number of turns per unit length, not per meter it is given per mm. Next it says, if 1 ampere current flows in the solenoid, the magnetic field strength at the center of the solenoid is. Fine. It's basically relation. What is our relation? Magnetic field due to a solenoid, due to a long solenoid is given as mu naught Ni, right? Mu naught Ni. Let us substitute the values. Mu naught is 4 pi into 10 power minus 7. N, number of turns per unit length, but it is given to us in mm. So it will be 100 by 10 power minus 3, right? I, current is your 1 ampere. How much are we getting it? When we simplify it, we'll get it over here. 4 into 3.14 into, this will be your 10 power minus 5 by 10 power minus 3. So B value comes out. This will be your, which option are we having? Any option? Yes, option 3.14 into 4 will be your 12.56 into 10 power minus 2. 12.56 into 10 power minus 2 Tesla, right? Which option it is? Option number 1. Yes, option number 1 will be a correct answer. Let us move ahead. Yeah. Next is a theoretical question. Two statements are given to us. Let us see one by one. Statement 1 says, Biot-Savart law gives us the expression for magnetic field strength of an infinite current element of a current carrying conductor only. What is our Biot-Savart law? If I have to write it, Biot-Savart law is given as mu naught I by 4 pi dl sine theta by r square. Yes, this is very much correct, right? This is dB. If I have to write, it will be due to a small element, we write it dB. So magnetic field due to a small element, Biot-Savart law gives us magnetic field due to a small element. Statement 1 is correct. Yes, no problem with this. Second, statement 2 says Biot-Savart law is analogous to Coulomb's inverse square law of charge q, with the former being related to field produced by scalar source. Yes, one thing is correct, that your Coulomb's law will be basically telling us about idea about the force and the field produced by the charge. Okay. Next, ideal, while the latter being produced by a vector. Okay. Now over here, if you read the question carefully, statement 2 carefully, it says Biot-Savart law is analogous to Coulomb's law. Both are inverse square in the sense, but it says with the former being related to the field by produced by a scalar source IDL. IDL. Now current carrying element over here is not a scalar quantity. We write it, if I have to write the vector form of this, it is given like this: mu naught I by 4 pi dl cross r by r cube. That means this is not a scalar quantity over here, and which in the statement they mention that the Biot-Savart law is finding out magnetic field due to the scalar unit. No, it is finding out due to a vector unit. So this over here, this is a wrong statement. Therefore our statement 2 becomes wrong, because Biot-Savart law does not find out over here. If you look at the second line, that field produced by a scalar source ideal. No, it's a vector source ideal. Length vector is, it is length vector, right? Fine. So statement 1 correct, statement 2 is wrong. Which option it will come? Option number 2. Option number 2 is our correct answer. Fine. Let's move ahead. Yeah. So the question we have is, in the product F equals to QV cross B, it is given QV cross BI plus BJ plus B naught K. Okay. If Q is equals to 1, charge is given to us 1 coulomb. Velocity vector is given to us 2 I cap plus 4 J cap. And magnetic field, force is given. Magnetic field also they have given, which is B I cap plus, is it visible there? No. B is B I cap plus B J cap plus B naught K cap. Okay. And the force is given to us. Force is given 4 I cap minus 20 J cap plus 12 K cap. Right? What will be the complete expression for B? Now this question is basically from your force on a magnetic force on a moving charge particle, and a magnetic force on a moving charge particle. What is our relation? It says force is equals to QV cross B, right? Anyways, charge is given to us 1 coulomb only. So V cross B, whatever is the cross product of velocity and magnetic field, that will be equals to force. So let us calculate the cross product of, let us write down the cross product of velocity and magnetic field, and we will compare it with the force vector which is given to us. Let us calculate V cross B. V cross B, to calculate V cross B, I am using the matrix method. What is matrix method? V cross B, first row it will be I, J, K. Second row it will be coefficient of velocity. What is coefficient of velocity? 2I 4J only given, or what? 2I 4J plus 6K cap. Okay, 6K is also there. B is correct. Force is 4I minus 20J plus 12K. Okay, velocity is given to us 2I plus 4J plus 6K cap. So in the second row, coefficient of velocity 2, 4, 6. In the third row, coefficient of magnetic field B naught. B naught. Let us write down. So V cross B comes out to be, if we solve it, we have I cap, if we do cross product, 4b naught minus 6b minus j cap, it will be 2b naught minus 6b plus k cap, we will get 2b minus 4b. Okay, let us simplify. Now we can further simplify it, or directly we can compare the coefficients. If we directly compare the coefficient, over here what is the coefficient of k cap? 12. Over there coefficient of k cap is minus 2b. So we can write down, I hope you can see over here this. So minus 2b is equals to 12. That implies b value comes out to be minus 6. Well and good. Now b value is minus 6. Any one of them, again we can compare it. So this is coefficient of I, which is 4b naught. I am doing it this side. So one is b value, we got it minus 6. Next I am doing over here 4b naught minus 6b is equals to coefficient of I cap is 4. So b value already we got it as minus 6. So this becomes 4b naught minus minus will be plus 6 is 36 is equals to 4. So 4b naught is equals to 4 minus 36, that is your minus 32. So b naught value is minus 8. Well and good. We got b value, we got b naught value. Let us write down magnetic field. Magnetic field is, ultimately it will come out minus 6 I cap minus 6 j cap minus 8 k cap. Right, now you can check the option. Do we have the option? This is our answer. Check option. Option number 2. Option number 2 is our correct answer, right? Yeah. So our question says, an infinitely long straight conductor carries a current of 5 ampere. Okay, long wire is there. It carries a current of 5 ampere. As shown, an electron is moving with a speed of 10 power 5 meter per second to the conductor. Okay, moving with the speed of 10 power 5 meter per second parallel to the conductor. That means this is the direction of velocity. Next it says the perpendicular distance between electron and conductor is 20 centimeter at the instant. Okay, calculate the magnitude of force experienced by electron at that instant. Magnitude of force. Now this is a question. We want to find out force on this electron. Which force? Magnetic force. How much is magnetic force given as? Magnetic force is given as QV cross B, which we can write QVB sine theta, right? Do we know the charge on the particle? Yes, it's electron, we know it. Do we know the velocity? Yes, we know it. Magnetic field, we don't know the magnetic field. From where is the magnetic field coming? This current carrying wire will produce magnetic field in its surrounding, and due to that magnetic field, this electron will experience the force. So how much is the magnetic field? If we see, magnetic field will be in outward direction, and magnitude of magnetic field due to a long wire is given as mu naught I by 2 pi r. Right, let us find out magnetic field. Mu naught is 4 pi into 10 power minus 7, current is 5 ampere by 2 pi into r. How much is our separation? 20 centimeters. So that becomes 20 into 10 power minus 2. Let's solve it. 2 times 10, this is 2. So B value comes out 1 by 2 into 10 power minus 5 Tesla. This is the magnetic field. Due to this magnetic field, the charged particle, the electron will experience the force. Now let us use our relation. Force magnetic is Q, charge on electron 1.6 into 10 power minus 19. Velocity of electron is 10 power 5. Magnetic field just now we calculated 1 by 2 into 10 power minus 5. Theta, sine theta. Theta is angle between velocity and magnetic field. Now if you will notice, magnetic field will come out to be outward direction, whereas velocity is in x direction. So magnetic field positive z direction, velocity positive x direction. Angle between them is your 90. So sine 90 becomes 1. I hope this point is okay. Outward magnetic field, positive x direction, velocity. So angle between them is 90, sine 91. So if we simplify it, it becomes 0.8, 10 power 5, 10 power minus 5. This comes out 8 into 10 power minus 20 Newton. So force on electron is 8 into 10 power minus 20 Newton. Which option we have over here? Option number 4. Option number 4 is our correct answer, right? Let's move ahead. Yeah. So next we have some graphs are given to us. Let us read the question. It says a thick current carrying cable of radius capital R carries current I uniformly distributed across its cross section. Okay. So basically a cylindrical cable wire is given to us. Its radius is R and it carries a current of I. Fine. Next it says the variation of magnetic field due to cable with distance small r from the axis of the cable is represented by. Now over here this is something that results we should know for this. The results of magnetic field due to a cylindrical wire for inside points using Ampere's law, the results are derived, and for inside points, that means when r will be less than capital R, magnetic field is given as mu naught I by 2 pi r square into small r. This is what the result for inside points. For outside points, that is r greater than capital R, magnetic field is given as mu naught I by 2 pi r. Right? Now you take a look over here. If you see carefully, we have to find out, we have to draw graph between B and R, right? So for inside points, B is directly proportional to small r, and for outside point, B is inversely proportional to small r. If we draw the graph, it will come something like this. This type of graph. Now you check it, which option it is. Option number 2 is our correct answer, right? Okay. Next question, it says a uniform conducting wire of length 12L, 12A and resistance R, wire length is 12A and resistance R is wound up as a current carrying coil in the shape of first equilateral triangle of side A. Okay. Equilateral triangle of side A. Okay. And second as a square of side A. Okay. They are asking us the magnetic dipole moment of the coil in each case is magnetic dipole moment. What is magnetic dipole moment? If let's say the current is over here I, okay, the current flowing in each case is I, we have to consider. So magnetic dipole moment, what is relation for magnetic dipole moment? Magnetic dipole moment for a current carrying loop is NIA. N is number of turns, I is the current flowing through it, A is the area. A is the area of the loop. Now let us see for this triangle case, magnetic dipole moment can be written as number of turns. How much is the total length of the wire? 12A, right? And 3A is the total length of one triangle. So basically how many turns you will get it? You will get 12A by 3A. Basically 4 turns you will get it. Current is I into area. Area of triangle, area of a equilateral triangle of side A, area of equilateral triangle will be root 3 by 4 A square, right? If we simplify it, what are we getting? 4 3 times. It anyways cancels out. So this one will be and 3 goes away. Next, so what do we get it? It comes out root 3 IA square. This is for the triangle. Next, for the square, again relation is this only, magnetic moment relation. So M is equals to N, number of turns over here. Thus over here total sides length will be your 4A and you have 12A is the total length. So how much it will be? 3 turns will be coming over here. 3 turns will be coming. So we can write 12A by 4A, for the square it will be 4A into current I, area. Area of the square. Area of square is A square. How much are we getting it? 4 3 times. So M is 3ia square, right? We have root 3ia square, 3ia square. You can check the options. Option number 1 gives us answer, right? Yeah. So our question is, a long solenoid of 50 centimeter length having 100 turns carries a current of 2.5 ampere. Solenoid question. Before this also we have done it. Let us see. So solenoid length is given to us 50 centimeter, and over here 100 turns are there. 100 turns, that is capital N is 100. Current is 2.5 ampere. They are asking us the magnetic field at the center. Now what do we know? Over here magnetic field is given as, magnetic field due to solenoid is given as mu naught Ni. N over here is what? Number of turns per unit length. So N, if I have to calculate, small n will be capital N by L, which will be 100 by 50 centimeter. 50 centimeter is 1 by 2. So you will get it 200. 200 turns per meter. Okay. So mu naught is 4 pi into 10 power minus 7 into N is 200 into 2.5, right? I can write it 25 by 10. It cancels out. We'll get it over here 4 into 3.14. This becomes your 25 to 50 and 500 into 10 power minus 7. Okay. So 5 4 is 20, 20 and 20. So 2 into 3.14 into 10 power 3 into 10 power minus 7. 2 into 3.14, 6.28 into 10 power minus 4 Tesla, right? Which option is given? Option 6.28 into 10 power minus 4, option number 2. Option number 2 is a correct answer, right? Let's move ahead. Okay, next question. This is NEET 2019 question. A cylindrical conductor of radius r is carrying a constant current. Okay, the plot of magnitude of magnetic field B with the distance d from the center of the conductor is correctly represented by the figure. Now if you notice, just 21 questions, repeated question, 2019, 2020 and same repeated question. Before this also we did it. The graph over here will be third. Already we did this question. Third option will be the correct answer. Repeated. So, but yes, fine. Third answer will be the correct answer. Yeah. So, the question is, ionized hydrogen atom and alpha particle with same momentum, same momenta, that is same momentum, enters perpendicular to a constant magnetic field. Fine. So, in a region magnetic field is given to us, and your ionized hydrogen, that means H plus, and alpha particle. Alpha particle is helium nucleus, that is helium 2 plus, right? Both of them are entering with same momentum. Fine. The ratio of the radii of their path is, we know that whenever a charged particle enters a magnetic field and moves perpendicular to the magnetic field, it moves in a circular path. The charged particle will be moving in circular path, right? So what is the radius of it? What is our radius relation? Radius for a charged particle is mv by qb. mv by qb. Momentum is given same for them. Magnetic field is same. So we can write down your radius will be inversely proportional to charge. So what can we write? Radius of hydrogen by radius of alpha will be charge on alpha by charge on hydrogen. How much is charge on alpha particle? 2, and charge on hydrogen, ionized hydrogen, will be 1. So 2 is to 1. 2 is to 1 is our answer. Option, which option is given? First option, right? Yeah. Question says, it is 2019 question. Two toroids 1 and 2 having total number of turns 200 and 100 respectively. So toroids are given to you. Basically number of turns over here is 200. number of turns N2 over here is 100, N1 is 200, and average radii are 40 and 20. R1 is 40 centimeter, R2 is 20 centimeter. Fine. Next it says what will be the current is same, current I is same for both of them. What will be the ratio of magnetic field along the two loops? Okay, magnetic field due to a toroid. What is our relation? Magnetic field due to a toroid is given as mu naught Ni. It is mu naught Ni. Small n is number of turns per unit length. Number of turns per unit length. Now, what will be the length of a toroid? It will be 2 pi r, basically the circumference. So, 2 pi r. So, our relation becomes mu naught capital Ni by 2 pi r. Now, over here, if you notice carefully, in both of them, current is same, है ना? So, we can write down magnetic field will be proportional to total turns by radius. They are asking us the ratio. So, we can write B1 by B2 is equals to N1 by R1 into N2 by R2. N1 by N2. N1 by N2 is 200 by 100. R2 by R1. R2 by R1 is 20 by 40. Right? 1 is to 2, 1 is to 2. Right? 2 and 2 cancel. So, our answer comes out 1. Answer will be 1 is to 1. So, first option 1 is to 1 is our correct answer, right? Please see the procedure, what it is done. This is your magnetic field due to toroid, and N over here, small n, is total turns per unit length, right? Let's move ahead. Okay, next we have a straight conductor carrying current I splits into two parts as shown in figure. Okay, this is our circular part given to us. Over here, current is splitting at this part. Current moves over here as well as current goes in this part, right? And current comes out. This is our current. Now, as you can see, the angles over here, this angle is your how much? Pi by 2. So, this angle will be 3 pi by 2, right? It will be 3 pi by 2. Fine. Next, it says radius of the circular loop is r. The total magnetic field at the center P of the loop is. Now, over here, if this is your current I, if you will notice over here, this part of the, if let's say total length is L, this will be your how much? L by 4. And this one will be your how much? 3L by 4. We know that current is inversely proportional to resistance. Current is inversely proportional to resistance, and resistance is directly proportional to length. Resistance is directly proportional to length. So, over here this one will have more resistance, less current. So, over here if this one has a length of 3L by 4, assuming that total length is L for this circular loop, if over here we have 3L by 4, current value over here will be I by 4. Whereas current in this part, in the smaller curve, will be 3I by 4, right? This is current distribution. Let's call this as your I1 and this is your I2. Now they are saying, find out the magnetic field at the center. Let us say, first of all, let us calculate magnetic field due to this smaller arc. So, B1 will be mu naught I by 2R theta 1 by 2 pi. I hope this relation is clear. Due to a circular arc, magnetic field at the center is given as mu naught I by 2R theta by 2 pi. So, over here B1 can be written as mu naught I. Current value is how much? 3I by 4 into 2R. Angle. How much is our angle? Angle subtended at the center is pi by 2. So, we will get pi by 2 into 2 pi. Pi cancels out. We will get 1 by 4. So, B1 value comes out 3 mu naught I by 4 into 4, 16 into 2R. Okay, equation 1. Let us look at equation 2. Magnetic field due to this, the larger section. Hai na? Over here, acha, one more thing we should see. Magnitude we got it. Direction will be outward direction. So, dot circle I am putting over here. B2. B2 will be The direction will be inward, but let's see the calculation first. Magnitude mu naught I by 2R. How much is our current? Current over here is I by 4, 1/4 only. So I'll directly write over here I by 4 into theta by 2 pi. Theta by 2 pi. How much is the angle subtended? This one is subtending an angle of 3 pi by 2. So it comes out 3 pi by 2 into 2 pi, right? So what can we write? This 3 pi will cancel. B2 value will be, this 3 will come out, 3 by 4, and this is 4, this is 4, this is 2 into 2, 4, 4 and 4 will become 16, 3 by 16 mu naught I by 2R. This is our second. Direction will be, turn your fingers in the direction of current, thumb will give you the direction of magnetic field, which is coming inward, whereas this one is coming outward. So inward, cross circle. Now see carefully, look at the magnitudes. 3 by 3 mu naught I by 32R, outward direction. 3 mu naught I by 32R, inward direction. B net 0. B net value will be 0, right? This part and this part both are producing same magnetic field but in opposite direction. Good question. I hope you understood it. Over here, the point that was supposed to be kept in mind, or we need to be careful, was that the current distribution was, we had to do the current distribution carefully over here. Remaining is just application of formula, magnetic field due to a curved wire. Fine. This is it. Let's move to the next question. Yeah. The question which is given to us is a 250 turn rectangular coil of length 2.1 centimeter and width 1.25 centimeter. Rectangular coil is given to us 1.25 centimeter and 2.1 centimeter. Number of turns are 250. Okay. It says carries a current of 85 microampere. Current is 85 microampere and is subjected to magnetic field strength of 0.85 Tesla. B is 0.85 Tesla. This is 85 microampere, 0.85 Tesla. So calculation 0.85 Tesla. Calculation will be doing carefully. Fine. Work done for rotating the coil by 180 degree against the torque is. Work done. How do we write down work done? Work done, basically magnetic field is present. Okay, magnetic field is present and the coil is rotated by 180 degree. How do we write work done? Work done is given as change in potential energy. What is the potential energy of a coil? What is the potential energy of a coil which is present in a magnetic field? Potential energy is given as minus m dot b, minus m dot b. M is the magnetic dipole moment, B is the magnetic field. So U is minus mb cos theta, right? Minus mb cos theta, and m value, we know m value is your current into area. Area over here, length into breadth, so it will be into area. I am writing as L into B. Fine. Let us see. So over here, work done will be U final minus U initial. Work done is U final. It will come out to be how much? Minus MB cos 180 minus MB cos 0, right? So over here, this work done comes out. This is minus MB cos 180 is minus 1, minus minus plus. This is minus minus plus. So work done will be 2 MB cos so 2 MB we are getting it, hai na? This is 1, this is also finally 1. So 2 MB, let us write down M. Magnetic moment is I into length into breadth, that is your area. Magnetic field is your, it is given to us 0.85. Let's substitute all the values. 2 into I, current is 85 into 10 power minus 6 ampere, L into B, which is your 2.1 into 10 power minus 2 into 1.25 into 10 power minus 2 into 0.85 Tesla. And one thing over here is given to us is the total number of turns is 250. When beta you will solve all this, when you will solve this, your answer will come out to be D option. What is our D option given to us? 9.1 microjoule. This is what it will come out. Hai na? Calculation is there. How to proceed with it? This is something that we need to be careful. Potential energy of a coil. Potential energy of a coil in a magnetic field is m dot b, and this is how we write down the work done, right? Finally, our answer will come out 9.1 microjoule. Fine. Let's move ahead.